So continuing on with the same compounded growth problem. So this was an original compounded growth problem. It says 30% per year, compounded monthly, compounded daily. Okay, so we calculated that. We're going to continue with the same interest, and we want to know how long it takes or how much needs to be invested to have $30,000 in 30 years. Okay, so it's going to make a difference depending on whether you use monthly or daily. Or yearly, so we can do it either way. So let's simplify this problem. Let's just say that we're going to end up with 30,000. We're going to start, well, we don't know the start, so I'm going to put that as X. Actually, I'm just going to put that as S, the starting amount. And the interest is going to be 1 plus, so 30%, and we'll just do this every year. Okay? And we're going to do this for 30 years. So this is just compounding once per year. So we're going to simplify that interest rate. Instead of dividing that interest rate up into months or days, we're just going to use that 30% once a year. Okay. So this problem here, we're basically solving for S. So this is not a log problem. We're just, although it has exponents in it, we're just solving for that. And we can do that very easily by just solving for S, by taking that $30,000, and this represents the percentage growth that we're going to get in 30 years for this 30%. Okay, so it's going to be 1.3 to the power 30. Okay, so I'll do this in two parts. So there's 30,000. I'll work out the denominator separately. So 1.3 to the power 30. Okay, this is going to be a lot. Okay, basically it increases by 2,619.99. So I'm going to round that to 2,620 times growth. Okay, so 30% per year is actually a very good interest rate. If you do it for 30 years, $1 will grow to $2,620. So that is the power of compounding. So if I then divide this, the starting amount I need to get this amount of money is I only really need to start with $11.45. Okay, so if I stuck $11.45 into a bank account that was earning 30%, well, that's a huge amount of interest, by the way. But if you had that and you left it for 30 years, you'd end up with $30,000. You'd end up with a 2,620 times increase in investment. So what interest rate is needed to earn this for this investment to double in 5 years? Okay, so if we want to double our investment, again, we want to put it into the exponential growth equation. So end equals start growth factor and growth cycles. Okay, so this in 5 years, okay, we want it to double. So we're going to say the end is 2 and we start with 1. We could do any ratio you want. We could do 200, 100, doesn't matter. My growth factor, I'm doubling, so I'm going to times by 2 every time I go through my growth cycle. And I want this investment to double in 5 years. Okay, so I want this, so I want, it said, first part of it asks, what is the interest rate? So I want to write it like this. So there's my interest rate, and I want this to double in 5 years. So this is part A of the equation. Okay, so I need to solve for the rate that will go from 1 to 2 in 5 years. I'm going to solve this. I need to use logs. So I get log 2 is equal to 5 log 1 plus r. Okay, so I need to, actually I don't need to use logs here, do I? Okay, I need to actually undo this. So I'm going to undo that power 5 with a root 5, with a fifth root. So I end up with 1 plus r. I can now solve for that, putting that in my calculator. R is equal to the fifth root of 2 minus 1, and that will give me my interest rate. So the fifth root of 2 is 1.148 or 149, so 1.149, and I'm just going to subtract 1, so I get 0.14. I can round that to 9, so 14.9% is the interest rate I need. So part B of this problem asks us, what is a growth equation using a growth factor of 2? So it's going to look like this. My growth equation is going to be end is equal to start. Okay. The growth factor is 2, and my growth cycles, well, I'm going to times by 2 every 5 years. So it's going to be years divided by 5, and that represents the number of growth cycles. So if I have 5 years, I'm going to multiply by 2 once. If I have 10 years, that's going to be an exponent of 2, so I'm going to double twice. So 2 times 2 times 2, etc. Okay, so this last one here for the exponential growth is you have a price of a bicycle. It's going down consistently. It's following a geometric sequence. Okay, so we're doing a geometric sequence going down. So it's going to go 12. Our R is going to be Tn over Tn minus 1. So I'm just going to use the first two terms. So I'm going to use T2 divided by T1. So 1083 divided by 1200, it's going to give me a growth factor of 0.9025. So that's my multiplier for each increment. Okay, just going to double check that that actually works for all the other ones. 966 divided by 1083. That's going to give me about 0.89. So we're going to round this to 0.90 and say that it's essentially, we're just going to round that. It's essentially going down by 10% or multiplying by 90% each successive week. So if we continue this, so we want to know the 21st week. So we want to know in the 21st week, it's going to be T21. So this is the first week, second weeks, etc. Okay, so we're going to find T21. We start with 1200. Okay, and we're going to apply that growth factor of 90%. And we're going to apply that, to go from 1 to 21, it's 20 times, or we can use a formula, 21 minus 1. Okay, so to go from the first term to the 21st term, there's 20 steps to get there. Okay, so applying this, we're going to end up with 1200, 0.9 to the power of 20, and by the 21st week, this very expensive bicycle has gone down to a price of $145.89. Okay, so this is how much, based on this geometric sequence, it's going to go down in that way.